Um, Hello everyone. This is an oral presentation about our CASA paper, AFF Dehazing, Attention-Based Feature Fusion Network for Low-Light Image Dehazing. I am today's reporter. My name is Zhou, come from East China University of Science and Technology. Our presentation is divided into 4 parts. The first part is the introduction of our task. The second part is the main contributions of our method. The third part is the proposed method. And then we show the experimental results and get conclusions. The last part is Q&A. The proposed method is aimed to achieve low-light image dehazing. Haze is a common atmospheric phenomenon and often lacks the qualities of the images acquired by the cameras. Besides, haze tends to appear at night, so images captured in haze conditions, especially at night, with low light often suffered from degraded visibility, contrast, and vividness, which makes it difficult to carry out the following vision tasks, such as object detection, semantic segmentation, and optical character recognition. The low-light image dehazing is a technique that aims to restore a clear, haze-free image from a single or multiple low-light haze images. Recently, many efforts have been made to solve the problems of image dehazing and low-light image enhancement. Image dehazing is directly mapping a hazy image to its corresponding clean target, while low-light image enhancement has been a well-developed topic in low-level vision for long. Obviously, these two tasks have been developed rapidly in recent years. However, current methods like the investigations on images dehazing and low-light enhancement simultaneously. These methods can achieve relative good performance on corrected images when removing a certain target type of distortion, such as haze or low light, but these methods are not effective in removing both types of distortions. A straightforward method is to solve the low-light image dehazing is to solve the dehazing and the low-light enhancement intent. However, there are numerous issues with such approaches. Firstly, the errors and the noises will be accumulated through the simple concatenation. Secondly, the two-step network doesn't fully exploit the correlation between the two tasks. Inspired by this, we propose an attention-based feature fusion network for low-light image dehazing named AFF Dehazing. Our AFF Dehazing contains 4 modules: image dehazing module, low-light feature extractor, fusion module, and the restoration module. The dehazing module and the low-light extractor are designed to extract haze-relevant features and low-light features. The fusion module is designed for blending these features. The restoration module is introduced for restoring a clear image from low-light haze image. As the images show, all AFF dehazing consists of two branches. One branch aims to obtain a dehazed low-light image. This is output of the dehazing module, and the other branch generates an enhanced haze-free image. Is that the final output of our AFF dehazing net? Now, the method proposed by us will be described in detail. We first detail the architecture of the proposed attention-based residual dense block. This is the unit block of our AFF dehazing. As the figure exhibits, ARDB contains a residual dense block, RDB, and an attention mechanism containing the channel attention and the spatial attention. In view of the fact that the features from different channels have totally different weighted information, besides, the distribution of haze in different patches also diverse. So the introduced attention mechanism can improve the discriminative learning ability of our ARDB. The framework of our method is shown on the upper of this slide. Our AFF dehazing contains 4 modules. The first is the dehazing module. The second is the low light feature extractor. The third is the fusion module, and the last is the restoration module. These modules function as follows. The dehazing module and the low light extractor are used as 2 branches of the dual branch, respectively, to extract the haze-relevant features and low-light features. The fusion module is designed for blending the dehazing and low-light features. The restoration module is introduced for restoring a clear image from a low-light haze image. So the output of our method can achieve low-light enhancement and dehazing. Since the dual branch are used, our AFF dehazing can avoid learning the mixed degradation all in one and enhance the details of low-light haze images. Our proposed low-light image dehazing network based on dual branch and produce 2 outputs. One is the dehazed low-light image JD, and the other is the enhanced haze-free image JE. And JD is the dehazed low-light image corresponding ground truth, and the JE is the enhanced haze-free image ground truth. L denotes the overall loss function combining the L1 loss and the perceptual loss, and the L1 loss and the perceptual loss are shown in this slide. The alpha, beta, and lambda in total loss are the ways to balance the 3 loss terms in total loss. Here, we show the experiments. We first briefly present dehazing benchmark datasets. After that, we conducted extensive experiments to demonstrate the power of our dehazing AFF dehazing net. Finally, we show the ablation studies. So the first is the datasets. Zhou proposed a nighttime image dehazing benchmark to address the absence of large-scale benchmark datasets. The dataset contains NHC, NHM, and NHR. NHR contains low light haze images and corresponding dehazed low light images and clear images. We randomly choose 4,000 images from NHR as training data and 100 images as testing data. We show the example in this slide. We also choose the PSNR and the ASIM as our metrics. Larger PSNR and the SSIM scores means this similarity between dehazed images and the ground truths, which means better quality. The AFF dehazing is tested on the synthetic datasets for qualitative comparisons with nighttime dehazing method, MRP, and 7 dehazing methods that include HL, PDN, AOD, EPDN, Grid DehazeNet, MS BDN, and FFANet. We adopted peak-to-signal noise ratio and the structural similarity index metrics to evaluate these methods. For PSNR and ASIM measures, we adopt ground truth as references. As shown in Table 1, the last row shows the dehazing results by our dehazing module. It is obvious that our method achieves best results in both PSNR and SSIM values on testing data. To further verify the performance of our method on low-light image dehazing, we compiled with the combinations of dehazing algorithms and low-light enhancement algorithms on synthetic datasets. The enhancement methods are 0 DCE and enlightened GAN. The results are shown in Table 2 and Table 3. We can observe that the methods using concatenation scheme will lead error accumulation and typically less effective, compared with the best performing combination for low light enhancement methods. Our method surpasses them by a large margin in terms of PSNR and SSIM. We also conduct the qualitative comparisons of different methods on synthetic and real-world images. Here we show the qualitative comparison of different methods on synthetic outdoor image. It is observed that most results suffer from color distortions. Compared with these algorithms, results restored by our dehazing module are closer to ground truths. In this slide, we show the visual comparisons on synthetic data. The results are obtained by combinations of dehazing algorithms and low-light enhancement algorithm 0 DCE. We can observe that when using the concatenation scheme, the color distortions and the artifacts are severe compared with other methods. Our results can restore a clear scenery. We also show the results obtained by combination of dehazing methods and low-light enhancement methods enlightened GAN. The results prove that our proposed method outperforms the existing methods for low-light image dehazing. And here we show the qualitative comparison of different methods on real-world images. Compared with other methods, our AFF dehazing can achieve better performance. Here we show the ablation studies. We conduct ablation studies on the effect of key components of our low-light dehazing network. We mainly consider the following four factors. The first one is the fusion module. The second one is the dehazing module. The third one is the attention mechanism. And the last is the residual dense block. It is obvious that all the four components are vital in our low-light image dehazing network. We also concern about the three hyperparameters in the method, as shown in the total loss. The results are shown in Table 5. It can be seen that the results that when setting the value of alpha, beta, and lambda equals to 1, 1, 1, 1, our AFF dehazing can achieve best performance. Okay, for the conclusions, we propose an attention-based feature fusion network for low-light image dehazing. The AFF dehazing contains four modules: image dehazing module, low-light feature extractor, fusion module, and the restoration module. The proposed attention-based residual dense block, which not only contains local residual learning and feature attention, but also adds the dense connected layers. Extensive experiments demonstrate the competitive performance of our AFF dehazing for low-light image dehazing. Here is our future works. We are plan to extend the low-light dehazing method to complicated video applications. Second, we want to enhance the generalization ability of the low-light image dehazing model. The last, construct a more reasonable dataset which contains more complicated things. Thank you for watching, and any questions?
Okay, thank you, Zhou. Yeah, so before everyone leaves, I sent the link to the Discord in the chat. So yeah, so if after the session we can join on Discord. But the session is not finished yet. Yeah, I still got one question. Maybe you can move back to the ablation study, your ablation study.
Oh, ablation study.
Yeah. So yeah, right. No.
Oh, sorry.
The table.
Oh.
Yeah. So I think from the PSNR and SSM, it shows that the most important component is the attention mechanism, right?
Yes.
And why not is not? I mean, why is not the fusion model? But it seems that the fusion model is the least important, right? Is the least important. I mean, if you remove the fusion models, the performance doesn't decrease much. But if you remove the attention model, it just crashes.
Thank you for your question. The fusion, because the fusion module can fuse the feature is extracted by the dehazing module and the low light extractor. So I think the feature obtained from these two modules are important for restoring a clear image, and the attention mechanism is the basic unit of our AFF dehazing. So it appears in the fusion module, dehazing module, and the low light extractor and the restoration module. So without the attention mechanism, our dehazing performance will be uh, the very poor.
Okay, but another question is the PSNR here is around 19, but I think on other tables it is around like 28. What's the difference between the models?
Because the ablation study is Chen on the um, the batch size and the epochs are different with other tables, but the hyperparameter in this table are all the same.
Okay. All right. I think so far there's no questions from the audience. Then maybe we can conclude this session. Yeah. Okay. Yeah. Thank you very much.